Yeah, thank you for joining, everybody. For those of you in the room that my back is to you, I apologize, but it's just the layout of this particular room. Today I'm going to talk about embedded programming with Rust. And what I decided to do for this talk is just have a little bit of a getting going, so a bit of a workshop tutorial kind of thing. For anybody that hasn't done this kind of stuff before, I'm going to cover some stuff like cross-compiling and how to set up your workspace a little bit. That actually is, in my opinion, the tricky part with embedded programming. A lot of the code samples we'll see today, there will just be a few that they're actually relatively straightforward and fairly easy. But I wanted to point out both the pitfalls and then some of the stuff that you have to know for embedded programming. Yeah, so just with the talk, basically, I'm actually going to start with a little bit of a demo, just so that people can get an idea of what we're talking about here. This is pretty much a hello world type demo. So we're going to blink an LED and we're going to turn on a fan. So that's your really basic, like you've got an LED, you want to do something with it, and then you've got a fan or a servo in a more general sense. How do you actually work with it? What are some things you got to know, especially if you haven't really worked with physical electronics before? Yeah, so I'm gonna start from that level, and if we want to get into some more advanced stuff for the Q&A at the end, then be happy to go into what I know. I've done a little bit of embedded programming before. I'm relatively new to it on the Rust side, but just one thing I think is really cool about Rust is it's the first kind of mainstream language that appears to be useful all the way from embedded programming. So basically like no OS, you're so close to the hardware, all the way up to like web programming. People are using it with WASM and you can run WASM stuff in your browser. So I think that's pretty neat. But to get started with the demo here, so let's see. Just gonna adjust this. All right, so we've got sort of your really basic setup for embedded programming. So I've got a microcontroller. So here I've got an Arduino Uno. It's a R3 for anybody that cares. And basically what we've got here is a dev board. And then this black splotch here is the actual microcontroller, which is something called an Atmega 328P, which is just a particular microcontroller that the Arduino folks have built a dev board and kind of a learning board around. And then we've got a pinout on the outside here. So these vertical black things are where you externally interface with the rest of the world from the microcontroller. And there's a few things built onto here. So there's a programmer. You'll see this connected with the USB cable. That's going to my laptop here, which I'm going to use to just upload a couple programs. And then on this breadboard beside us here, I've got a motor driver, which is just going to run this fan. So to start with, I don't know if it's possible to see, but there's a little blinking LED on this board. So that is a program that I have running right now. It might seem a little bit underwhelming, but a blinking LED is kind of the hello world of the embedded programming world. So you're actually controlling something. And with an LED, of course, it's really just on and off. So that's your, is it actually working? So you usually blink it so that you can actually see it doing something. Because if it's solid on or solid off, you don't really know if your program's working or if it's just stuck. So I'll change program now, and we'll go over how you can upload programs to Arduinos. But in hopefully a moment, we're going to see the fan turns on. So the fan, I'm just doing the same thing. I'm turning it on and off. Again, this is going to be a very simple program. You don't have to understand much Rust syntax to understand these programs. But I wanted to show these first so that people have this in the back of their minds while we go over the rest of it. So with that, and turn it back to the LED just so it's less distracting. So with that, I will define embedded programming because my experience, it actually does mean different things to different people. Wikipedia defines it basically as I have on the screen here. So it essentially means that it's really low-level software. So it defines it as software that's written for things that are not typically thought of as computers. So I mean, fans, obviously, that we have here, but also, everything from your thermostat to your car to the SkyTrain if you're here in Vancouver. All of those have embedded controllers all the way through them. And they do all kinds of tasks from, monitoring electrical systems to, if you've got ABS brakes in your car to, our little demo here, of course. And even most things that are computers actually have lots of little microcontrollers in them. And they perform various functions too to interact with the hardware. Because that definition is pretty broad, some people think that basically anything that could be a full computer but is embedded in something else is embedded programming. Others think that you specifically have to be on a microcontroller or something that has very small amount of RAM, CPU power. For this demo, I'm going to show it on the Arduino. So there's actually no operating system running. So there's no Linux, there's no Mac, there's no Windows. It's just instructions that are going into this device, and it will do some stuff, some simple stuff. But that's what I'm going to use for this this talk. I'm going to define it as this tiny system that we have here. And I mentioned the hardware that we have. So our parts list is not massive if you ignore all the wires that are connecting things together. So we've got a Arduino Uno R3, and I'm just going to link to the docs here so that people can see what the hardware docs look like. So Arduino has excellent page here, but I just want to go to pinouts. So immediately, as soon as you start talking about embedded programming, you're talking about hardware, and hardware is going to start becoming your main focus. Oftentimes, the programs that you write in embedded are relatively simple, actually, especially if you've done really advanced things in Rust or any other programming language. So you're going to spend a lot of time looking at hardware. We'll go over a little bit of what some of these things mean, but you'll notice that lots of the hardware documentation, immediately you've got a bunch of things where it's labeled. There's a bunch of pins here, and each of these labels have both a name that we're going to use in the programming, but then also some of the more advanced features that this board might have. So, anything in orange here where it's like D12, for example, that represents a pin, but some of these pins also have special capabilities that if you turn them on in your program, you can use them in special ways. So the orange means that it's a GPIO, which is a general purpose input and output. Basically, it means that depending on how you can configure your device, it either could be input or it could be output. Can't be both at the same time, because it's either your microcontroller is going to control the voltage on that pin or something else is, and you can't do it at the same time without shorting your device and ruining it. There's also a number of other things you're going to see. So on the left-hand side here, we see a bunch of these ones where they're green. So we've got ADC 0 to 5. ADC is analog to digital converter. So it basically can read analog signals, and then you can work with them more as like a floating point type of thing as opposed to a digital representation. And then on the left-hand side, we've got two other acronyms, I2C, or you'll often hear it also I2C, which is a particular two-wire communication protocol. And then there's one SPI that is a four-wire communication protocol. So immediately we're going to start thinking about pins and wires, even though we're writing software. And that's your reality of embedded systems. I also want to look at the motor driver just briefly. So what we've got here, this is a L293D. And again, I just want to briefly show the data sheet, which in a programming context seems like, well, why are we looking at circuit data sheets? But again, the focus here is really you were going to use our microcontroller to control this little piece of hardware, which is a chip, a power supply for our motor. And that's what allows us to turn it on. We can't directly attach the motor to the microcontroller because the microcontroller can't actually output enough power in any one of its pins. So we use the microcontroller to tell this driver to output the power required for the motor. And I just wanted to show people this because, again, especially if you haven't worked with electronics before, this can look very intimidating. But a lot of circuit data sheets kind of look like this. And from a programmer perspective, it can be kind of useful to know the various levels. But what you want to find in these data sheets, even if you don't know that much about programming, is first of all, logically, how does it work? So of course, physically, we've got this little black thing with a bunch of metal pins coming out of it. So what do those pins do? And I won't go through the whole data sheet, but you can see that the pins are usually labeled some kind of logic diagram. So in this case, we can see pins, there should be 1 through 14, I think. And not all of the pins may be connected on all devices. I think in this one they are. But I'm just going to scroll down. So in any physical device, the physical layout is often extremely important to note. And you'll notice that each one of these pins, they have a name. So there's a 1A, a 1Y, there's this heat sink and ground pin, 2Y, 2A, VCC. Those may be weird terms, but most of them will be defined somewhere in this data sheet. With the exception, I'll just point out that ground is, so in electronics, that's your ground terminal. So that's going to be your, call it your negative terminal in this case. So those all will need to be connected together. And then VCC is power. So that's going to be the input power to this device. And the rest of these pins will have descriptions here that say what they do. I'll skip most of them, and here we go. So as a programmer, things that you need to know about this are really, what is your function table, which is going to be, what does this device actually do from a digital logic point of view? And what you can see is that there's a column for A and there's a column for EN. EN is really just like, it's an enable. That's where EN comes from. So in this particular circuit, I've just, I'd say hard coded, but the way that you hard code in hardware is you just connect a pin to a power in this case. And your A input, whether you're high or low, so it's high voltage or low voltage, which could be like on or ground, gives you an output on the Y terminal of, again, high or low, or Z in this case means high impedance, which you can see it defines it as off. For people doing electronics, high impedance means a little bit more than just off, but it just says that the current's not going through this. And really that's the main thing as somebody writing software needs to understand about this data sheet. You know, if these circuit diagrams look very foreign to you, that's perfectly okay, because what you need to keep in mind is really just this function table. So is it high or low? Is it on or off? And that's what we're going to use to drive the motor. So obviously when it's on, the motor will drive, and then when it's off, the motor won't. So you can skip a lot of the information if you either don't know what it means or don't care about it. And there's examples of applications and how to connect them together. Of course, if you need to dig into exactly what this does, because either you're debugging something or you're trying to design something from scratch, then there's a lot of information in here. But we're just going to stick with that pin description. And then lastly, the motor that I showed with the fan. It's a really cheap small motor. It operates at 3 volts to 12 volts. It's a DC motor, which means I don't need a fancy circuit. I just need a power on or power off. And then it goes up to 25,000 RPM if I didn't typo that. So it can go relatively fast, suitable for a fan, not suitable for some lower speed applications. Like if you were trying to do something precision, this is not the motor to use. Again, your application really determines what hardware you pick. which is really going to determine how complicated or simple your programming is. So I'm showing the Arduino pin out here again. And I just wanted to highlight in red that we're going to use these pins D10, D9, D6, and D5. So just these 4 pins, and they're the ones, I don't know if you can see, but they're physically right here on this side of the board. The 2 other wires that are going across, those are power supply wires. So that's what's providing power to the board. And again, this is just one little snippet out of the data sheet there. But what I've highlighted in red is what I've implemented. So on the motor driver, I've connected pins 2 and 7 to the microcontroller, and pins 3 and 6 are going to the motor. So that's what we can use to drive the motor. And if you look, this M with the circle, that's your motor, and the arrows here show that it could be spun in either direction with this case. If you look at the ones on the right-hand side, that would be for a single direction motor, but we can do it in 2 directions. Okay, so I'm mostly done with the hardware now. We're gonna start talking a little bit about some Rust and how we compile programs for this and how we work with that. But there's sort of just the overview of this system. So again, there's really 3 components essentially. There's a microcontroller, there's a motor driver, and there's the motor itself. Okay, so LED blink program. This is our Hello World. It's
a bit small.
My formatting is messed up.
You might want to make it, yeah, a little bit.
Okay.
Maybe if you go into slideshow mode.
I don't know if that's capturing it for everybody.
It's like
That's good enough. Okay. So this is basically Hello World. I'm at first gonna just skip this: no STD, no main, panic halt, and Arduino HAL entry. We'll go over them in a few moments, but this is what it looks like. And if you'll excuse the formatting for the peripherals here. So this is what it looks like to actually drive a pin on here. So we've got, our first line is that we've got a bunch of these peripherals. Of course, Rust, as we know, is a safe language. So the peripherals are all put into the structs that we have to take, because of course these pins are essentially the equivalent of global variables, because the pin is a physical object, and for each pin there's only one, and it has a state. It's either high, low, or it's going to be in that high impedance mode, which is what you use for reading. You've got a list of pins because there may be other peripherals that are not pins associated with this. So the next line here, we've got our pins, and there's a macro to extract that out, gives us this object. And then we're specifically going to take pin D13, which if we were to go through the Arduino datasheet, we would see that pin D13 is the one connected to the device, and we have to convert it into an output pin. So the hardware abstraction layer that we're using here is basically forcing us to choose if it's an input pin or an output pin, and that gives us our LED value. And we're going into an infinite loop. So our program is really just this tiny infinite loop that's an LED toggle with a delay of 500 milliseconds. So it's very, very simple program really at its core once you unpack the pins from the abstraction layer. And there's a couple important features here that I just wanted to mention before we move into like no STD, no main. First is that you can see with our main function, we're explicitly not returning from this function. And this might be a big difference, especially if you're used to programming, command line tools or things that like they don't last forever and they exit, which they do on a normal system. Because we're on a hardware system, we don't really have the option of exiting from main because there's just some code. So what would an exit from main even mean? There's no operating system, so there's nothing to hand control back to. So we actually have to handle the entire lifetime of a running program on this device, and there can only be one program at a time.
Question, what happens if you don't put the exclamation mark there for the signature?
So the macro might put it there for us, but you're actually going to get compile errors in the general case.
Oh, okay.
Because so our entry point is not the usual entry point, meaning that where our program starts, again, we don't have an operating system, and all operating systems define an interface for the program at a very low level, like in the, how is the program laid out in memory level of how do I start this program? And they have a special symbol. It's usually called start. That there's actually a little bit of setup that your program goes through before main gets called. It's not big, but it usually on a typical like laptop or server, it's going to take any dynamic libraries you're linking against. It will bring those into a memory space that your program can see and interact with. Your OS will set up memory pages and assign them to your program. It'll load anything from disk, like the program executable itself, etc. Those all happen before main starts. But in this case, there is nothing that happens before main starts. Our main is the beginning of the execution of this device when we turn it on. So that has to be handled. And you'll notice almost everything, even if it looks fairly simple, is now special. So we're not using like time sleep here. We have to use a specific Arduino HAL delay millisecond. And the reason is, again, because now we've got physical hardware that we're interacting with at the lower level. So time sleep is actually an operating system level interface where you can't directly call sleep because sleep tells an OS like Linux or Mac or Windows that my process doesn't need to do anything for a while, do other stuff in the background. But there is no equivalent here. So what delay milliseconds is actually doing is setting up an internal clock on this microcontroller, and it's just setting an interrupt so that it will literally do nothing until the 500 milliseconds is up. Right. So no operating system, and I mentioned the startup stuff already. So one of it is that we have no STD. So what this means is that we have no standard library. So all the stuff that you know and love from the Rust standard library is unfortunately gone. Now, before you panic too much, there is another library that's also kind of the standard library, but it's called core in Rust. And the core library is very similar to the standard library. And there's a comparison here. So I'm going to link a couple times to this Rust embedded book, and I'll link to it at the end. This is a great resource to read through. But so there's some key things, and they call it no STD and then STD here. So of course, STD has heap. So these are all your dynamic memory. So strings versus strs, vectors, etc. So those exist in the standard library, and they rely on dynamic memory. And that exists because you have this operating system that does it for you. But when you're in the no STD mode, there's nothing that handles that for you. And you can actually see with a little asterisk here, it does say that you can have dynamic memory if you use the alloc crate. And then you have an allocator, like this particular one is an alloc Cortex M. So Cortex M is a particular type of processor. And so you start having to use processor-specific libraries that can interact with that specific piece of hardware. So every piece of hardware is going to be different, is another slightly challenging thing. It means that you got to read a lot more crates and a lot more documentation than you might be used to, because instead of just doing, a vec new, suddenly you have to go figure out how the allocator works in this Cortex processor, or in our case, the Atmega 328P. Similarly, I already mentioned, but there's none of the regular collections, so they're gone. Again, there's other crates that help you fill in these gaps, but by default, they're not there unless you specifically put them there. There's no stack overflow protection. So Rust does a really good job generally for if I make a function that calls itself and I make a mistake, so it calls itself an infinite number of times, eventually you'll get a stack trace if I were to run something like that on this laptop, and it would say, oh, you had a stack overflow. But in the no STD world, there's no runtime associated with it. There's no operating system, and so we don't have those types of capabilities. And again, there's no init code before main. So you can do init code before main in regular Rust. You can't do it in embedded. So there's just a lot of things that really you can't do. But this libcore is available. And the libcore, have the link. So it actually has most. Yeah, okay. So it actually has most of the things. It looks very much like the standard library, but with specific things missing. So you'll notice there's no collections module, but otherwise, if I also open up STD and I scroll down, you'll notice that the module list in STD and the module list in core look very similar to each other, but you have to know that you need to use core. You can't use STD, and if it's missing in this module list, then unfortunately you can't use it. So you will notice backtrace is another one. So that's the one where if you have an assert in Rust and it prints out a nice backtrace to tell you where and why that happened, that exists in standard. It does not exist in core. So these are challenges that we have when we're working in embedded systems. You basically don't have any helping hands. The system's doing nothing for you. You have to handle it all yourself in code. So toggling pins is great, but as soon as you start doing more advanced things, you'll start noticing that a lot of common crates don't really work for you anymore. Fortunately, there are many people interested in this, so there's often alternatives to most of the common crates. But you have to go through the extra effort to find what you need. And very similarly to the no main. So the main, normally there's a little bit of loading that happens. In embedded case, there isn't. So the beginning of your main is the exact beginning of your program. And here we have to register which function is our main. So I actually could have called main anything in this case, as long as I had this Arduino HAL entry. This macro here is actually what tells the compiler that this particular function is where I want to start. Because otherwise, main is just a convention. And it's a very common convention on x86. But as soon as you move away from common operating systems, it could technically be anything else. But I personally recommend still use the name main because it's less confusing. And finally, panic halt. And that's related to if you've ever dug into what happens when you have an assert and you get something like the nice traceback that Rust will print to the console. That's a capability of a feature called panic. And there's a lot of info here. Again, this is a link into the embedded book, but the short version of this is that they have built-in functions. So panic abort basically just says if you panic, you're just stopping. So, pardon me. So if you panic, your CPU is just going to stop, and there's no recovery. Again, there's no operating system, so there's nothing to hand it back to. Any questions so far?
I guess my question is, do you have to have like the breadboard and everything to blink the LED?
No, the breadboard contains the driver for the fan. You don't need it for the LED because it's actually on the board.
Okay.
Sorry, my voice is kind of going. So in our particular case, We've got this Arduino CPU. I mentioned a couple times this Mega 328P. It's got its own instructions. So the low-level binary that you have to load in to the memory on this device is different than like the x86-64, which a lot of laptops have, or AR64, which is Mac laptops, and then most phones these days. That's your ARM CPU. So it's different. And one might ask the question, why have something different? Like, why not just use an ARM CPU? So there's a few reasons, but when you get out into like a car or something like that, one of the good reasons why you might use a different device, and again, I'll just zoom in enough. So these are all various packaging for Atmega 328Ps with maybe some specific peripherals attached. But I want to show the prices here. So per unit, it's $2.52 per. So if you've got to build devices with millions of these and you don't want to pay large amounts of money in terms of your manufacturing costs, you can buy these one-off from, I'm on DigiKey here, which is just one common supplier, for $252 each. Or if I buy 6,000 at a time, again, this is kind of for manufacturing, I can get them for basically $2 each. And that's nice and inexpensive. It's a lot cheaper than you'd find for an ARM device. So it's still very much worthwhile to put these in things where cost is a concern. And I also have just a quick example of what I mean when I say like the instructions are completely different. So you can't just run like an ARM compiled bit of code on here. Okay, so this one, unfortunately, so this is the Godbolt Compiler Explorer. If you haven't seen this before, it's a super useful tool for just like visualizing what's happening with assembly or what goes into your program. On the left side here, I've got something. This is actually in C, so that's why I apologize. That Rust Meetup. Why am I showing C? I swear this is going to be the only C that you're going to see
No pun
this
intended.
time, and no pun intended. But on the top here, so I've got x86. So it's a little bit crowded, but this window that I'm scrolling here. So this is the x86-64 assembly for this function, and basically. You don't really have to know what it means, other than it could be useful to know that this is the actual multiplication that we see between our two numbers. And that's what it looks like. So just know that it's whatever that is, 7 or 8 assembly instructions long. If I now switch to AVR, which is the instruction set that we're using, so we can see there's, I don't know, some globals here. There's this square that now has a bunch of different instructions. You'll see there's also this label definition that's here. And overall, it's actually much longer, which is just a factor of this particular instruction set. But it's completely different. So there's no way that we could load the compiled upper program on our CPU and still have it run. We need it to be targeted to this AVR thing specifically. And especially if you come from a higher level language where it's either not compiled or not compiled to machine code, you don't have to think about this as much. Or, in fact, perhaps most people are designing for servers that they probably have a same or similar instruction set to your local CPU. So you never have to think about this until you get to something like embedded, and then you do. So that's yet another challenge. Fortunately, Rust, as we all know and love, makes this very easy for us to set up. We basically just put some TOML files and make sure that we have the dependencies installed, and we're pretty much good to go. But that process of compiling for some other CPU that's not the one we're currently developing on, it's called cross-compilation. So with Rust, you need to make sure that you have the correct toolchain installed. RustUp can make this very easy. There's also some external tools for particular things. If in the Arduino case, I do actually have to have a linker
installed that's specific to that platform. But once you have that, it's actually very easy. And I've just got some links here, so I won't go through it in a lot of detail. But if you go to the AVR HAL crate, which is one that I'm using, it has instructions for installing on Ubuntu, Mac OS, Windows. You basically just copy paste this into a terminal, and you're good to go. So I won't dwell on that too much. Rust up is very nice because you can add targets for cross compilation with just rust up target add and then whatever the target is. And I'll show you the supported ones officially. Now, this is where you have to kind of know what it is that you're developing for. But so Rust has officially, so this is the Rust Lang website now. It's got 3 different tiers of recognized targets. So tier 1, they say guaranteed to work. Basically, this is the stuff they run their CI/CD on when they make changes. So you'll see it's got Linux on both ARM and the 32-bit and 64-bit x86 CPUs. Of course, it supports Apple stuff as well. Tier 2, they say guaranteed to build, so they might build it, but they don't run all their tests on it. This is a slightly bigger list and includes some stuff that you may or may not have run into before, like PowerPC or this Long Arch 64 architecture, and some operating systems. So in addition to the CPU architecture, you also need to know what operating system you're going to run it on because they have different capabilities. So FreeBSD versus Linux with the Musil library instead of glibc, for example. And then they've got a much longer list of partially supported. So they don't have all the host tools, for example. There's a big list here. I'm not going to go through them all. And there's tier 3, which are AVR shows up somewhere here in the tier 3. Again, it's a very large list. There's an awful lot of things out there. So I won't go through them all, but they exist. And the way that we tell our particular crate which one we want to use is cargo config toml. So if I just go to, so this is just my my repo here that's got everything that I need. So I can configure what I want this to compile to with a combination of our cargo toml and then a hidden directory that's .cargo. And you can put so just using the words that I have on some of the slides. So we have targets. In this case, I'm saying that I want to compile for this AVR at Mega 328p. It lets us put the actual definitions for this in a JSON file. You can get a JSON file pre-made for you that has all those declarations inside the AVR HAL crate that I briefly popped up on screen. And I can also say that when I'm compiling for this target arch AVR, and this is a pretty cool feature, we can tell cargo run to execute another program, and it calls it a runner. So in this case, we're going to use this ravedude. And ravedude is a program, it's written in Rust as well. It's specifically designed to be a runner for just doing the upload to the AVR device, which is attached to my laptop with USB. So it finds the correct USB one to use.
Yeah, we don't see.
Oh, I'm sorry.
Those programs.
Maybe if I share the whole screen. Okay. Yeah, there we go. That's what people are looking at. Okay, so this config toml. Yeah, so there's your target. You can specify your JSON file for all the stuff to do with your target. And that you'll usually get from either a manufacturer or if you happen to be working on CPUs and you design CPUs yourself, maybe you make one of these, but typically they're already made for you. And this is the Rave Dude. So you can set your runner to run Rave Dude with these arguments whenever you do a cargo run in this repository, which is good for us because, of course, we're uploading it to the Arduino. And then I have to do an unstable here where we're linking against core, but that's just all that shows up in here. So that's where most of the magic comes in.
So do you use Rave Dude for just Arduinos, or does it use for like all sorts of different technical?
So it's anything for the AVR series of processors. So Arduino is one of them, but there's a bunch of other ones that share the same architecture. Some of them are not Arduino, but it's specific to that. There are probably other tools for other ecosystems. So you were mentioning like the STM32
Right, yeah.
family of devices. I believe those have their equivalent. But if I want to just upload, when I use Rave Dude, I can just have a cargo run, release. I've got multiple binaries in here. I've got the LED one, I've got the fan one. So I have to specify which binary, but I just hit enter. It compiles everything. And
so that's like flashing the program to the.
Yeah.
Okay.
So that's what's happening here. So you'll notice that so there's a compile step, and then the run step is actually, there's an additional board and there's a programming. So you can see it's taking this particular file and it's trying to put it on dev CU USB modem 1101. That just happens to be what my OS said that the AVR device was mounted under. Obviously, it wrote it. I just want to point this out. So my program is 262 bytes long. This is tiny. And the actual device here, I think it has like 16K of memory. That's it. So it's all very, very tiny. But sometimes people don't realize, because if you make a hello world in Rust, it by default, it's like about a meg or something like that. A lot of that's actually the standard library, and it's the other stuff that's kind of hidden from you that takes up a lot of the space. When you get rid of that, then you can get programs that are just as small as C. And sometimes people go, all Rust programs are big relative to C programs. It's mostly because C programs, they use a lot of shared libraries where Rust tends to statically compile everything and link it in. But C programs tends to be, you keep your core in your main program, and then everything else is shared libraries that get loaded. That's why they're smaller. It's not because C is more space efficient than Rust is. Rust, you can produce absolutely tiny binaries if you wish. Yeah, so just so people know about that. And yeah, thanks for bearing with me. We're getting pretty close to the end here. So there's other tools that you can analyze the outputs. Just things like file and NM will tell you that it's compiled for the proper CPU architecture, and then you can actually see the symbols. I already mentioned Rave Dude, and the link here is to the actual Rave Dude repo. It has some additional instructions for advanced stuff. But if I were to do this manually, there's a different program called AVR Dude. And without Rave Dude, I would have to copy paste this whole long line in. So I could run this by hand. Obviously, cargo run is so much nicer. So thank you to the all the Rust people to make this super nice. AVR Dude is not a Rust specific thing. That's what I would do if I had written this in C and I needed to upload it. I'll say by hand, but obviously the tool does a lot of the actual work for me. So cargo run is absolutely the way to go. Arduino Rave Dude's great, but there's probably a tool for whatever platform that you want to design for. Okay, and I think this, yeah, before just the resources where I've got a bunch of links, this is kind of the last thing. So I mentioned pins. So the program that we looked at before was very small, very simple. Actually, maybe I'll also pop up the actual fan line. So it's a tiny bit longer, but not much. It's still got all the same things. You'll notice I I manually implemented the panic handler, and believe it or not, an infinite loop is a valid definition for this. But the basics, the peripherals, and then grabbing the pins is the same. These pins were the ones that I highlighted on the Arduino diagram. And in order to actually run it, so I was setting the LED as well, just for demo purposes. It's a little counterintuitive, but in this case, setting everything to high actually turns it off. That's just the way I wired it. And then setting the motor to low actually turns it on. Just that's the way I wired it. And it's so it's off for 5 seconds and then it's on for 2 seconds. So that was the fan turning it on and off there. But these pins, like how do I know into output? Where does this come from? It can be a little bit frustrating because if you actually just look at Arduino HAL, it won't look like there's a lot of these definitions into it. So how did I know that like pin D13 has an into input? And that's where I just wanted to show people embedded HAL crate. It's not that big, but it's kind of like SerDes in the sense that it's got some generic higher level traits. And for whatever particular hardware you have, you're going to pull in a crate that implements the specific trait. So for an input pin, the embedded HAL has your required methods is high, is low for an input. That's how you could read from one of these pins. So I only had output pins, but if I did into input instead of into output, I could have read from a pin, is it high or is it low? And of course, it gives you a result of a bool. And similarly, with output pins, we use the set low and set high in my program. And then there's a provided method if you have set low and set high. So this is a base fundamental crate that you'll see most of the other hardware crates are built on top of. So usually in practice, if I were to port this program from our Arduino CPU to like the STM32 CPU, the main thing I would change is instead of in my cargo TOML pulling in, actually I didn't show cargo TOML, but instead of pulling in the AVR HAL crates, I would pull in the STM32. And this should look familiar to you if you've programmed in Rust. So I just have 3 different binaries. I'm using a Git checkout for the Arduino HAL repo. But beyond that, it's just a couple of dependencies. And also specifying here that the panic is abort, which tells the compiler not to generate a bunch of the infrastructure around like getting tracebacks, which is not supported on this device. So
is LTO usually true for embedded programs?
By default, it's not, but there's really no reason not to turn it on for an embedded program. So first of all, they tend to be very small. So the main reason not to turn LTO on in the first place is typically that it takes a long time when you're compiling. But for these, I mean, both because this particular example is very small, but also because you're very resource constrained. As I mentioned, it's something like 16K of it's not disk, but basically disk in this case, and it's got a smaller number too, I think, for its working memory. I'm remembering those numbers right. So you do want it to be as efficient as possible, typically, and things like turning on LTO and the opt level is S, which in this case, the mnemonic is that it's for small. So it's optimizing for a small amount of code generated, as opposed to the most efficient code, because we're very memory constrained. Certainly in our case, we don't have high performance requirements. So that's an easy trade-off for us to make. That is pretty much the end of the talk. Just highlight a few things just to get people going. So the embedded Rust book, which I linked to a couple times.
I don't think it's showing.
There we go.
There you go.
So the embedded Rust book I showed a number of times. This is a great resource for getting going for more advanced Rust stuff. So everything I showed was actually also safe Rust. Maybe I should have highlighted that a little bit more. Is these hardware abstraction layers, or HALs, are awesome because they completely hide any of the unsafe bits from the higher level. And really, other than just working with your peripherals, either, whether it's the I2C 2-wire protocol, or the SPI, or the pins themselves, or anything like that, the abstraction layers are designed in such a way that pretty much all your stuff gets to remain safe Rust, which again is a huge improvement over something like C in this case, where you could easily mess something up, and debugging in this case is much harder. So that is actually a very nice feature of the hardware abstraction layers. I also wanted to point out that there's crates that exist like Embassy for async code. So async is another thing that you need to have some stuff kind of set up for it. Rust's async story, people find it really annoying compared to some other languages when you're working with really high level code. But the reason why it is kind of annoying is that it's designed in such a way that you could get it running on an OS-less device. So you can actually get async running even on these like tiny single-threaded CPUs that don't have memory paging. They don't have multiprocessing. There's no like advanced hardware that goes into that. So you can get Rust async going even on these devices. So Embassy is a well thought of crate that provides a lot of the infrastructure for doing that. And then I also mentioned that there's no standard library. So a lot of like your vector, your hash map, like all that stuff is missing. So there's other crates like Heapless that they provide equivalents to those, but they have the cost. So here's their VEC example, and you can see that. So the cost to that is that they use a fixed amount of memory. So in this case, the second number is that first is, of course, still just whatever type I've made my VEC. But the second number is how many elements of space does my VEC need to take up? And the reason is because it's now using stack space for your vector allocation. So it's still a resizable value, but you're putting your maximum number as part of your type. So there's crates. Heapless is, again, a well thought of one that helps you do that. But there's others, and there's also ones that give you more advanced types. And of course, it's obligatory. There's an awesome embedded Rust repo. Again, I won't go through it, but there's a huge list of resources for all kinds of things. So on screen, here's your STM HAL crates, for example, and there's a different one for each different vendor variant. So again, won't go through them all, but there's lots of stuff here. Basically, if you want to get into any kind of embedded programming, I'd say pick something cheap that you can get and really just start playing around with. Just doing some simple stuff like getting a driver for your motor and doing some motor stuff can be rewarding. It can be more complicated than a fan example. I just wanted us to not get too bogged down in the hardware aspect. But there's lots of great stuff out there, and sky's the limit. And that's the end. So thank you, everybody, for listening.
Thank you. Yeah. Thank you. I guess, does anyone have any questions? Sure, go ahead.
Can you just expand a bit on the development and development process of doing this stuff? Like, for example, you've got a program and you just want to simply determine that it got onto the Arduino successfully and is actually working there successfully. What do you have in terms of feedback mechanisms? Like, if I want to know that the program that I've written has executed down to, say, line 10 or something in the program. Like, the light's not coming on and the light is the last instruction in my program. Right. So how do I do the debugging stuff?
Okay, yeah. So there's starting with the most generic, of course, like anything you can write unit tests for, write unit tests for. Designing your stuff so that it can be tested without necessarily running on the actual hardware is absolutely essential for like once you get beyond sort of trivial systems like the ones that we showed here. So there are other things as well. So most devices have, they call them programmers, but they're actually a physical device that you have to buy it. And what those allow you to do is hook into capabilities of that physical device in order to do some of the things that we would look at with a debugger on our machine. So whether I might launch GDB or LLDB to debug a Rust program interactively, like on the laptop, you can use these programmers to get a similar type of functionality.
Yes, please.
But it's typically like it's not the same. I don't have a good example to set up here, but
The programmer, as you're calling it, is another alternative physical device.
Yeah.
And it allows more insight into what it's doing as it runs your different program. And you are able to, I guess, look into it, and you can see consoles on your laptop that are showing you this.
Yeah. So depending on the exact one, there will often be some specific software that comes along with it too. So there's a protocol called JTAG that it does this. It's fairly slow, but it does this like shift all the register values out so that you can see all of the internal register values, for example. And that goes back to the like assembly level. Like you can actually look to see what's in each register. And when you're in embedded, you're more likely to get there in terms of you care about what each instruction is actually doing. But another way, which is probably what most people do, and certainly what I would be doing next if I had a one complicated program I wanted to debug here, is their simulation and emulation tools. So one common one is called Shinu. So it's an actual, I think you'd call it an emulator, but it can actually run CPU instructions that are not for your host CPU. And so you can simulate that, but then still have tools that are more friendly to a laptop development environment.
Maybe look at a log file.
Right. Yeah, because you typically don't have a disk on a lot of these. So they usually have what's called EEPROM. So it's electrically erasable, programmable, read-only memory, which sounds like an oxymoron. But what it is when you're putting the device into programming mode, you can write to it. But in regular operation, you can't. So that's one of the reasons why like firmware updates for things usually have to restart whatever device it is, whether it's your car or your 3D printer or whatever, just because it has to put it into a special mode so it can write to these pieces of memory, and then it pulls it out of that mode again and then goes into the
Is that part what's challenging? Yeah, I have my program written, but just the debugging and feedback mechanism, those two lots of hurdles. So that's what
Absolutely. So you verify as much as you can off the device, and then there's really no equivalent to a print statement for these. So another thing people can do is like on this device, for example, there's a I2C. So that's a very simple serial protocol that can get information as like characters off of your device, for example. So your kind of like logging example could be, like ship this data into my I2C bus so that some other external thing that I physically attach to it can read that and then print that on the screen and so on, right? And that's kind of your printf style debugging, which as unfortunate as it is, might be what you're stuck with, because some of the others, like the programmers, can be very expensive. JTAG is slow, depending on the exact features of your device. Like it may be very slow to use those types of things. So hooking up to like an I2C device might be the fastest iteration time.
Did you encounter that type of problem when you got this one?
No, because any mistake I made, Russ just told me I did it wrong.
So you were able to write Rust and just move it to Arduino and you got like,
Yeah. Now these are pretty simple examples. Like as you see, like they're not complicated examples.
Yeah.
But,
still, I could see, because if you don't have that breadboard wiring done correctly or something, then
oh yeah,
it's
it's
not gonna work.
so as soon as like I set up the breadboard at home and then I put it in a little box and I like carefully like shifted here after testing it all at home, right?
Oh man.
Because
Double unplugged wires,
yeah.
that's not fun.
well, and also if you make a mistake with the wires, like smoke can come out of it and it won't work again.
Yeah.
Right, okay, right, you fried
Yeah.
your board. Right. Yeah.
And so if something is fried, then it's fried, and you have to buy a new one,
Right, back to Amazon.
right? So it's it's in some ways it's less forgiving than writing it for a server or a laptop. It's, but at the same time, it opens up some new areas that makes the pain worth it.
So when that happens in frying the wires, it was then you actually setting the hardware up, or
Yeah, because if I were to unplug these and reverse them, I might permanently damage the chip.
so you see we have like GDB to debug it. So in Rust, is there any like kind of
You can use GDB.
Yep.
Like the Rust embedded book actually talks about using that, and I think they also talk about semi-hosting or something like that as well. Have you done that at all?
So I don't know exactly what semi-hosting is, but in environments where, like, let's say you're lucky and you do have enough memory that you can run multiple programs on whatever your embedded device is. So let's say it's an ARM device and you've got megabytes of memory available, which doesn't sound that big, but that can be a luxury. You can actually launch things like GDB on the device, and then you can do remote attach.
and you can set the breakpoint on source code level.
Yeah.
Okay.
Actually, you can even try that out on these. So let's say
Oh, we should probably read the chat messages as well.
No.
What they say. Yeah, so someone's talking about using OpenOCD, which can be used for remote debugging in some contexts.
And when you're done with that, I do actually have an example of a programmer from a different chip manufacturer.
Oh,
yeah, sure.
So
Actually,
this one here is from the Espressif manufacturer. So this side over here is actually a USB cable that plugs into a PC.
oh,
And then on this side, you'll see two little ribbon cables. The small one is actually tiny little 6-pin that can be used for programming. And then this bigger ribbon cable is actually a 10-pin that's a JTAG interface. So you can actually use this to plug to a little circuit board that's Espressif specific. And you have to use this particular dongle that knows some of the details of how to connect to it. So you'll see a similar thing will be like manufactured for each different chip manufacturer. They have their own tools and often their own specific hardware. So if you plug this into like the AVR chip, you would have a bad time But with this one, you can often say run an OpenOCD instance on your chip, and then actually connect GDB through OpenOCD through this to whatever your hardware is. And then hopefully the hardware on that side is connected correctly. It'll have been wired up that way.
Yeah, that's cool.
So way easier to just have it on your all running on the host. But if you're doing embedded and you're not running on the host, then you need some sort of bridge.
Yeah.
Are there ever, a basic question, ever like any operating systems with embedded program? Is it always because of time and memory constraints and stuff? It's always that system.
Yeah. So, like back to the definition I had at the beginning. You know, I've definitely worked on products where there was like a Linux operating system, but it wasn't for a thing that you would think of as a tool, and people would call that embedded. But in that case, it's kind of the easy version because yeah, you can just run everything like you SSH into that device, and you can run tools that were packaged into it, which could include a debugger. And then you just work with it the same way that you work with something on my laptop or so.
Yeah, we had another question in the chat that just asked which embedded Rust book is recommended.
So it's rustembedded.org/book, and I presume we'll post these slides, so you'll find it in the resources section. I would probably start with the online resources. There's a lot of blogs out there too with how to get started with various, especially the common platforms. So just a Google search would probably pull up good first steps for any particular one. Yeah, so I didn't cover it, but for example, the Rust Embedded Online one, like it has a big section here about how to use Keynote. Again, it goes through like how to set it all up and do remote debugging on it. Yeah, so we can launch Keynote, and then here's your GDB remote. So you can do a target remote, and it'll connect the report to the simulated machine. So there's like a GDB server and a GDB client, and the client's running on your host, and the server's running on the simulated device, and then you can use that to interact back and forth.
Can you put this Arduino thing in the context of, is this like a play toy that allows you to experiment? Or is this something that you could potentially make as the basis of a product? Like if you had a customer that wanted a fan that could turn on and off, you got that breadboard thing, you got the Arduino, you know what I mean? Like, is that what this is about? Is this like a place to experiment, or is this actually something that you could use to make some kind of simple hardware product?
Yeah, so the Arduino boards themselves are a bit more of the experimentation side, I would say, or prototyping or rapid prototyping. But the microcontroller actually pops out of it. And then there's other form factors. So this one is a dual inline package. So there's two like long rows of pins, and it can go into the breadboard. But there's also there's VGA, ball gate array. They're designed to be soldered directly onto a board, like a PCB. I mean. And so once you're done with this prototyping phase where your hardware looks like this, you might have somebody or yourself go and design a PCB, and then whether you do it yourself or whether you have some company do it, you could pick a different form factor. And there's many, there's, I just listed two, but then you could put that device on that board, and it could be a real product that you ship.
Yeah, maybe I can expand it on it a little bit. I think Arduino, the CPU for Arduino is usually very relatively slow, like in low performance. So for this one is for ESP32. this board is actually, they designed this board kind of particular for Rust. The board is called DevKit-Rust-1, and they designed it kind of for you to experience Rust. And this is their C3 CPU. I think the performance is kind of equivalent to like probably M3 or something like that, or M4. I think can have 4 to 8 megabyte of flash and storage. Memory is probably
Actually, if I could just show the folks that are on the bridge here. So this is the device that he's holding up here.
yeah.
So you can see.
We can't see.
Can you see me?
No, we see. Oh, maybe I
can
see. No, because it's his mic that's working, so we see him.
If you
Jonathan.
look at Aaron's screen, if you pin him,
Should I go to Jonathan's?
Oh, yeah, switch to
Maybe it's
Aaron's.
easier to go to mine, I guess.
Right.
There
So-
you go. Thank you.
So this is the device that we're talking about here. And the actual microcontroller is this shiny bit. And then the rest of this is support electronics. And I think I see an LED. Those look like a couple buttons. There's a USB on the end. So it's in some ways kind of similar, but the pins you see, they're just these little rings on the side. So that's designed either to be soldered directly to or for through-hole pins. So you could place this down on a device and then have it soldered.
Yeah.
Thank you.
So it's nice that you can wire this GPIO out or any interface like I2C or SPI out, and the CPU itself is actually on this board on the upper part. This tiny bit is itself kind of a module. The CPU is inside it, and it include this module include Bluetooth and Wi-Fi. So basically, when you develop your product, you use this pin to wire all the interface out, and then you develop your functionality. If it's done, you can just use this module in your final product. So you don't need this board, but you use this module. It's easier than you kind of grab the CPU and then directly mount it in your own board. So your board will still kind of have this module, but it's much easier. Like it's still surface mounted, but I think it's easier than the CPU itself, like inside this module. Yeah. So I think for this kind of CPU, you can really make some useful product, like real product, probably like do more than the Arduino, like 80 mega CPU can do. Inside there, yeah.
So what does this all kind of look like when you, I guess, put it into like an actual device? Like, I don't know, say like a Google Home. Like, I guess you'd have to like put batteries in it or something, and then you'd have to like wire that to the controller.
So
And then
you start getting into like a full system, or right, like a full like electronic system. So a bunch of that, yeah, it's more of a manufacturing and electronics type question, but absolutely.
Okay.
So like the Google Home, I can't remember if they were battery operated or plugged in.
Yeah, I don't
But,
know either.
Yeah, they're typically a lot of devices. Yes, there's some kind of power supply. So there's usually like wires coming in that have a voltage difference across them, depending on your application. That could be 3 volts, 5 volts, 1 volt, 47 volts or 49 volts. Like there's other sort of weird standards.
Right, but this thing doesn't have one. Like it doesn't have a
Right. So in this case, our Arduino is being powered by my laptop through the USB cable that is plugged in. So it's pulling the power from the laptop, and there's a power supply on that Arduino board that is taking whatever the USB is outputting and converting it into, I think it's 3 volts required for the microcontroller. And then I have it wired up for 5 volts is going to the breadboard. So the power supply on there internally has, they call them rails, but really they're just wires. So there's probably a wire that's set at 3 volts relative to a ground, and there's a 5 volts relative to a ground, and there's pins for each one of those. So I've used the 5 volts because that's what the chip told me I needed to go to the breadboard, and then that's what's going into the power in of the motor driver.
But like most like real products wouldn't have like a breadboard attached.
No,
inside, right?
absolutely. So that chip, that motor driver would be on a PCB. So on here somewhere on the actual, well, this is an Arduino board, but you would design your own.
Right.
And it's actually very cheap to design your own. That's maybe another one of these like hidden secrets is, yes, you got to go learn a bunch of tools that are specifically designed for laying out PCBs, but the printed part, so PCB is printed circuit board, the printed part kind of indicates that they're actually very cheap, especially if you don't need too many metal layers in them. It's well within, like for a small one, absolutely within like hobbyist costs. Like I don't know the current values of like a board that size, but like think less than $100 for like probably a simpler end of the design with a few layers. Of course, you know, if you're designing, you know, like a really, really high-end product with lots of technical specifications, like the boards that go into these laptops, for example, that might be much more expensive. But for hobbyist or, you know, low performance applications, they can be quite cheap.
Okay. So would you say that I guess the GPIO pins are sort of like the bread and butter of what gets these like external devices to kind of do their thing?
Yeah, because even if you are connecting things on a PCB, like you've decided that you like your design, you're going to integrate it into a single device, single board. So the GPIOs are still what you're using, and they're just not put to, they call them pin headers. So the things that stick up that the wires are going into is called a header. And so you don't have to have that. They could just, the wires that go from your microcontroller can go, you know, somewhere else directly to the thing that you wanted to plug into. So if my motor,
I should point the camera at this stuff too.
yeah, so if my motor driver were instead, say here, it looks like there's kind of an empty spot. So if that were here, then it would actually be soldered in to this board. And instead of the GPIO pins going to the vertical pieces that I've got the wire sticking into,
Right.
there would just be a small wire inside this board that goes directly from the microcontroller to this thing. So it would just be directly connected.
Oh,
It wouldn't have to go through like wires like this.
So basically, you need to design your own PCB board. You use the KitKat or something like that to round your PCB board, and then yeah, like you said, that nowadays there's some manufacturer that you can just upload the PCB drawing and even the BOM, the bill of material, and usually these manufacturers stock a lot of frequently used component, and if you don't use some kind of rarely used component, they can even just they have all the price on their website, and then they can just give you a code, and they can not only just make the PCB for you, and they can even put all the component on the board, and you kind of have a final product.
Especially like if you're willing to wait, there's ones out of China. I don't have any good ones to recommend because I haven't used them myself, but there's ones out of China that I know you can basically say, here's my board design, here's the list of where all the things should go on my board, send it to me, and you know, you have to wait for something to get manufactured and shipped from China, but say in a month, you know, you can get an actual like finished device that's like, here you go, here's what you asked for. And again, it's more expensive if you've got a bunch of components that are putting on. Obviously, you're going to pay the cost of the components, and you're going to pay a premium because it's not a mass manufacturing; it's a custom thing. But it's still within the realm of tinkering.
Yeah, I guess that's what I'm asking, because not having done any of this stuff, when I think of like, okay, I could make a website. Maybe I had an idea, right? I'm gonna make a website. There's in some dream sequence, it may have some practical utility for someone out there and you can make some money.
Right.
In this case, I'm just trying to rationalize, like, why am I tinkering? Can I tinker and potentially make some piece of hardware that can be sold?
Mhm.
I guess.
One of my friends made an automated cat feeder that he can
Ooh.
control.
What?
Like I've seen him log into a server from remotely, and he can control his cat feeder just because he felt like it.
Well, that's amazing.
Yeah, for sure.
Yeah,
I need that.
that's the example, right? Yeah.
Well, and really, it's like it's just like pure software. So pure software, like the sky's the limit. You know, your imagination basically, and your ability to like pull things together for like a website type of products. You know, is going to not determine your success, but it's going to determine whether you can build something and get it out there. And then, you know, if your idea is good, maybe people will use it. As you say, you might make some money. You know, it's the same thing with embedded typically, but it's going to be physical products. So, you know, like in this room, we've got a clock on the wall. So these days, there's probably some battery with a little motor, with a little, like some, it's not going to be an Arduino, but it's going to be some really cheap, really tiny, either microprocessor or just a little ASIC device that, you know, obviously like somebody designed that, and then it probably goes into, you know, if you go and whatever your home goods stores and you look around, there's 50 clocks on the wall. They're probably half of them using the same chip on the back end. And designers come up with the, you know, pretty physical parts on the front, right? But yeah, like if you've got, you know, personal projects, like I've seen people make little like robot arms that move stuff just for learning, but you could have something like automatic blinds. You know, you could actually take almost this design, right? Because it's a single motor. You know, does it pull the blind cord? Assuming the motor is powerful enough. You know, it could raise and lower blinds, for example, or something like that.
So there's a path.
Yeah, and then you can get more complicated. So you know, if the most complicated version of this might be something like Boston Dynamics, right? With their you know, very advanced
robots.
exactly, right? But I mean, really, at the end of the day, like, yes, there's tons of fancy algorithms and math and whatever that makes those robots work, and it's super cool. But there's also a bunch of, I'll say, relatively boring, you know, just little sensors and control systems that go into that, and all of those are going to be controlled with, you know, little microcontrollers, pieces of hardware. That, yeah, you know, like somebody had to design it. You know, so
Well, I guess realistically speaking, I guess almost like from the purely software side, like coding these programs for these devices, so the sky is the limit. But at the end of the day, you're still limited by like voltages and all the other physical.
Yeah, exactly.
Physical parts. So, like, I guess this Arduino is not powerful enough to be used in something like that. One of those Boston Dynamics robots.
It's certainly not for the main control system. You know, this is a low frequency device, so compared to even your phone CPU, you know, it's very, you know, physically it's maybe the same size as my watch, and my watch is probably you know, I don't know, 100,000 times faster than it.
But it's affordable as a result.
But it's very
Right.
affordable, like as
Okay.
we said, like
How much was it?
it's $2. It's $2 or something for the actual microcontroller, and for the dev board and everything, it's about $20 Canadian. If
So
anybody's,
you get started for $100.
Yeah.
And this can make a cat feeder.
yeah,
Good,
you,
yeah.
you
Cool.
come up with some designs for it, and get some physical parts, and then figure out how to portion out the amount that the cats get. And
I worked for a company in the past that had conceptually something similar, but instead of the GPIO turning on a fan directly, it went to a relay that they then hooked up to a large pump, and they would actually pump water in like swimming pools. And then they had various sensors that could have other pumps that would dispense chemicals, and they had temperature sensors and like pH sensors, and could connect it all to some custom hardware with the screen and buttons, and you have automated water chemistry control. But what's the difference between like a giant pump, yay big for a pipe that's that big, or a fan? From our perspective, you just take one little pin and you set it high, or you set it low, and the chain of events goes on.
Yeah, that's also a great point. The programming isn't necessarily that different for those devices, even though physically, like, it's a very different scenario. But the other thing that I liked about what you said is that there's all kinds of sensors for all kinds of things that you can get. I only showed like a simple motor, but yeah, you can get everything. I mean, you can get temperature sensors, you can get infrared imaging sensors, you can get
IMU
pressure sensors, you can right, yeah, you can get things with accelerometers on it, GPSs, electrically sensing things. Like,
is it better to have those, I guess, peripherals like on the actual board itself, or like separate? Because I noticed that there's like the LED is built into the I guess PCB here, but not this fan, obviously. Like, what are the trade-offs there?
right. So the main trade-offs are going to be, once something's physically integrated into that board, it's more difficult to replace it as an individual component. So hypothetically, if this were like an actual product, you'd probably still want the fan separately, because your failure rates for your fans are likely different from the electronics. So
Yeah,
for sure.
Thank you for coming.
Yeah, thanks for coming.
Yeah. Bye.
Yeah, so you're going to want your components that are more likely to fail to be easily replaceable, and you're going to make certain design decisions around that. On the other hand, having everything integrated as a single package will typically mean like fewer mistakes when people are putting them together, because as cool as robots are, like, a lot of products really are still physically built through human labor or assisted human labor. So the fewer steps you have in that, the easier it is. And if it's on a board, there's things like they're called like pick and place machines. So machines can basically do all of these components by themselves without human interaction. So the more you put on the board, probably the cheaper it's going to be, fewer mistakes, etc. You can automate the testing and construction, and the overall product might be a little bit cheaper to do it that way. But of course, you lose the flexibility. So for this demo, right, like, I'm going to go home and I'm probably going to take this apart. I'm going to do something different with the motor. It's not just going to be a simple thing. So I might build a little car next, or whatever, like whatever it is I decide I'm going to do next. So obviously, the ability to take it apart is valuable to me, but I'm not selling this. I'm just tinkering.
Right. Okay, cool.
Another aspect to consider is the actual physical requirements or constraints of the device you're building. So say you need a temperature sensor for sensing the outdoor temperature. You might not put that directly on the circuit board right next to the CPU, because it gets hot and it will throw off your reading.
Yep, that's there's lots of physical constraints. That would be a good one. Another good one is power consumption. So especially once you get into like Internet of Things type of devices, so remote sensors and stuff. I even heard, or I looked at a use case once when I was in university, where people were actually embedding sensors into concrete.
What?
So physically, the device was inside concrete, and of course, you can't just like get it out. You can't replace parts. And it was for stress monitoring bridges, I think, was the application. So
it would help for bridge maintenance. So basically, you could have a thing that you could, like, some guy would drive up in a truck and have like a reader, and the reader would output enough of a signal that it could wirelessly pick up enough power, because there's no battery in this thing, or there wouldn't be like a long-lived battery, because bridges hopefully last for 30 years plus. And yeah, so that it could read the stresses from a particular sensor type that it had, and it was just inside the concrete. So in that case, being ultra low power is much more important than any kind of performance, for example.
Interesting.
That's an incredible use case.
It actually was. I was
Really,
pretty
yeah.
mind blown that actually works.
Yeah.
Yeah, it wasn't me that was doing that. It was somebody else talking about their research when I was in university, when I was a grad student. And yeah, I was pretty mind blown.
Yeah, that reminds me, another common application of embedded systems we often don't think about is like a hotel room RFID card, right? Often those, if you were to peel it apart, you'd see there's an antenna around the edge. And I guess a credit card can be a similar example.
Yep.
And the credit card reader or the hotel door reader actually emits radio waves that power the antenna, then actually generates just enough power to power that tiny little processor that's in the hotel room card. And there's some memory on there and some encryption algorithms to ensure that the keys that the door expects are the keys that are actually present in the card.
Wait, you're telling me that these little boards are like inside of things as thin as like a credit card?
They're even
Double
extremely
NFC,
small, right?
right?
They're not actually these
Yeah,
boards,
company.
but they'll be a different version of that.
Yeah, so yet another interesting thing about this, like you see the size of the circuits there on the table, but the actual size of the chip inside of it is like, it's only like a couple millimeters, maybe. Most of that package is actually just empty space.
So most of this big long thing, this microcontroller, is just empty?
Yeah, it's probably filled with some like plastic material, and there's wires that go from each one of those pins to the chip, and the chip is probably somewhere right in the middle of it. But yeah, they're very tiny. The next time your credit card or whatever expires, I would encourage you, actually, because you're supposed to destroy them. So you know where the like gold pins are on the top of the credit card, right?
Right,
The,
yeah.
the chip part. So cut near there and just like shave off little bits, and eventually you'll actually see the little chip that's embedded in. You can pull it out, and it'll be this tiny, like 2 millimeter square thing. You need tweezers to pick it up, probably.
Oh, wow.
But that's actually how big these are.
Oh, okay. So they really are micro. I guess that's the micro and microcontroller mean.
And in many cases, we're limited by the packaging. And I guess that's another. So the dual inline package, like with all the pins in a row there, they're great for breadboards, but they're horrible for space density. So that chip now takes that amount of space. But well, people on the bridge probably won't be able to see, but if you look at this one, this little black square there, look how many pins that one has.
Looks like it has, like,
This one. So that's a surface mount device, and that probably has twice as many pins as the really big chip does.
oh wow.
But the internal chip is probably the same size.
Interesting.
So that's another thing that can save you money. You can make physically smaller boards if you have denser.
Right, but then you would probably have like less memory and less resources to work with.
Same capabilities of the chip.
Oh wow.
And actually, as they get smaller, some of the economics of the electrical operation part work better, because you need less electrons to charge a smaller wire than you do a bigger wire. So especially for digital, where you're not switching too fast, I have to start being very careful about how I say this. It can just overall be more efficient to go smaller. As frequency goes up, you start getting emissions effects, and you go into transmission line engineering, which is actually a subset of electrical engineering. So you have to be careful with the speeds of these things, but
Emissions as in like like dangerous emissions?
No,
or
no, no.
what?
Emissions in the sense that you get two wires that are right next to each other and you try switching one of them at really high speeds.
Uh-huh.
The wires at high speeds will couple to each other. So some of that signal will go from the first wire to the second wire.
Oh, okay.
And it'll start
Interesting.
messing up your signal. So
Ah.
it'll cause noise.
Right.
And anyway, so there's transmission line engineering. It's called that because the effect was first seen on like power transmission lines. And it's the reason why thunderstorms sometimes make power outages, even if the lightning doesn't actually hit anything,
Oh.
is because the waves coming in, like the EM waves coming from the sudden change in current with the actual like bolt of lightning, is enough to couple onto those lines and cause like fuses and stuff to.
Because any line actually basically is an inductor.
Oh.
It-
Wow.
It's just it's the induction is very small, but when your frequency high enough, everything is an inductor actually.
Huh.
Everything's an inductor, everything's capacitor.
Yeah.
So again, not to get too much, I didn't really want to get too much into the electronics, as this is a more of a programming venue. But yeah,
Right, yeah.
there's a like, so just if we're going to say that, it's probably worth saying that with some of the correct peripherals, like you can make radar out of these things. And that's how radar works, is that it sends out pulses of EM signals that bounce off of stuff. And you just listen for it to come back,
Interesting.
for example.
A
So do you have
very-
like a background in like engineering or electronics or something?
Yeah, my undergrad was in engineering physics.
Oh,
And then
okay.
my master's was actually in, well, it was electrical and computer engineering. But it was focused more on fabrication. So electromagnetics and microwaves, I think, shows up on my master's certificate.
Yeah, because I was wondering like how do you like best get into this stuff? I guess you're suggesting the Arduino here, but
Yeah, Arduino's STMs, like it depends really on what you'd like to build. So if you want to build some advanced electronic stuff, I mean, there's also big electronics communities, you know, people that just tinker with stuff. They've got home labs and they do lots of soldering and they build lots of PCBs themselves. You know, people that do like wireless and antennas at home, like the ham radio operators. Some people build their own radios, for example. So you can get into those communities if that's what you're interested in. If you're interested in, you know, building cat feeders and things like that, you probably don't need to go into that level of advanced electronics.
right. Hello.
Yeah, and I think if you actually want to get into radar, I think they actually have like kits to help you build your own radar, like a small radar.
Oh, there's like a radar kit you can buy?
Yeah, to build a small one, so you don't actually need a
Wow.
license.
Yeah, I think from like SparkFun and stuff, you can actually buy just a radar module. And I think Arduino has one that's like you see the wires are all just vertically stacked here. I think you can literally just plunk it down on top and it's designed so it fits together and you get a radar system.
And there are also sensor they got time of flight. It's a bit similar to radar, but they just use kind of light. It emit light, and then it is reflected light, and it's not just one point. It can have a kind of metric of receiver, so it can kind of detect an area, not just a deep distance with one point. And so it's a bit similar to radar, but we do not use.
It's actually, so anybody that has an iPhone out there, you turn on the, like if you're in the selfie mode and it focuses on, you may or may not know this, but it's actually using LiDAR. So there's like a little, call it a laser, that goes out and it's kind of scanning what's in front of it. And that's how it can detect where your face is, even in low light.
Oh.
Because there's an AI aspect of it. So if you put it in like portrait mode, the blurring the background part of it is AI. But where it the reason why it accurately knows where your face is versus where the background is this other tool.
See you.
And it's just built into your phone as part of that.
It's actually from ST.
Oh,
ST, they keep at the bottom their PO kind of by sensor. They say they use it. People even use it for the coffee maker to detect the level of the water in the water tank. So when it can detect when it's lower, you can send up the signal.
so for the iPhone example, like you said, it's using an AI. Is that AI like actually built into the device, or is it just like making a request to some server to like? calculate
It's
that?
actually so the newer Apple devices, anyways, they have what they call tensor units in there. Basically, it's
Oh,
the same type of stuff that you'd find in a GPU, but it's specifically designed to run some of their little AI models.
Okay, I guess that
And-
makes sense.
And
yeah.
those AI models are specifically designed so they fit inside of those devices on a phone, and they don't use too much power because, of course, you're not going to be too happy with your battery drains really fast.
Right. I was thinking that it seems kind of impractical to like actually like stick an AI onto your
Yeah.
device, but yeah, I guess if it's done hardware.
And using AI as a broader term, like machine learning might be a term people like a little bit better for these applications. They're not like the LLMs, like the
Yeah,
ChatGPTs.
the generative stuff.
Yeah, exactly. So those ones are huge models, many input and output parameters. But a lot of the ones that, some image processing, things like that, those can actually be much smaller and much simpler, so that they run on a phone just fine.
Okay.
All right. I
Well,
think that's it.
Yeah.
Thank you.
Thank you very much. This was
Yeah,
great.
we're over time. I didn't even notice.
We're definitely over time. Well, thank you everybody for joining, and hope you guys all have a good night.
It's a pleasure. Thanks for presenting and hosting.
All right, and I guess next time I think Chester is going to be doing a talk, so look forward to that.
Eagerly, right?
Is that in December or January?
You said December.
December, okay. No, I couldn't remember if it skipped
Oh, we
December.
also moved up the December
Right.
meetup as well. Just
Okay.
yeah,
Sounds
just in
good.
case. Yeah,
Sounds
All
good. No worries.
I'm gonna stop the recording now. All right, see you.
All right, bye.
I don't-